This is a question that's hard to make entirely precise. And that's intentional because it's not only precise questions that inspire us to pursue knowledge. But it turns out that this question, in fact, in some sense, I think is very old, right? So it concerns us in a very immediate way at the moment in many aspects of physics and mathematics. But you could say that it's been asked in different forms by intellectuals, philosophers, mathematicians and physicists from very ancient times. For example, I show here, this is actually the entrance to the Mathematical Institute in Oxford. And what they've done is they've reproduced this inscription that was supposed to be at the entry to Plato's Academy in Athens. And there, I hope you can see it in that photograph, what's on that sign. Let no one destitute of geometry enter this building. Right? So in Plato's Academy, geometry was supposed to have been an essential prerequisite for any further study of any subject at all, in some sense, philosophy and mathematics for sure, but even for ethics, to know what it is to live as a proper human being, Plato seems to have thought that it's essential to know geometry. So there are many interesting accounts of lectures he gave on seemingly human moral topics of inquiry, but in which he started talking about mathematics and puzzled his audiences. So this is also, so in this form, people like Plato certainly thought about geometry as being an essential ingredient of understanding all of existence, and certainly of understanding the makeup of the universe. Some of you may know that the Greeks had very specific ideas, maybe not mathematical ideas in the modern sense, but relatively specific ideas about what makes up the objects of the world. People argued about whether the fundamental element is fire or water or air, etc. And they tended to think that those objects, in fact, were made up of these objects up here on the screen, sometimes known as the Platonic solids these days. These are the 5 possible regular polyhedra in 3 dimensions. Right? And many of the scientists of those times thought that the basic elements like fire and water and so forth were made up of these shapes. So the point is that in answer to the question, is the universe geometric or algebraic, I think people around the school of Plato would have given the unambiguous answer that is geometry. Right? And in a sense, that's a very natural answer. Many of you will have studied some physics or chemistry or different aspects of theories about the makeup of the world. And if you think about it, much of the theory is actually geometric. Right? So Greeks thought about the way the planets revolved around the sun in the solar system. This was much more made very precise in the 17th century during the period of the scientific revolution in Europe by people like Galileo and Newton. And if you look at their conclusions, what were they interested in? They were interested in things like, how does an object move when you apply a force to it? In fact, they drew conclusions like planets going around the sun follow ellipses. Right? So geometry was really the basic language of describing natural phenomena. So the idea that the universe is somehow geometric may be a very commonsensical one that appeals to basic intuition of the way we think about the world. But in fact, even in those days, there were people like this. Some of you may have heard this. Pythagoras, who lived, in fact, maybe around 150 years before Plato, he had this very famous dictum that all is number. Have the students here, have you heard about this at some point? Maybe. You know? So Pythagoras is supposed to have said all is number. And if you're like me, you might have wondered what he could possibly have meant by that. You know? It was a metaphorical statement, right? And a poetic statement expressing his conviction about what is really fundamental in the makeup of nature. Right? People say he was inspired by musical instruments. The idea that harmonious sounds come by vibrating strings whose lengths are in very simple rational ratios, right? like if you shorten the length of a string to a 1/2, the frequency will double. And so you get a sound that's 1 octave higher, and if one string is 1.5 times the other, then you'll get a harmony of the 5th degree in the Western system of harmonics and so on, right? So this is supposed to have inspired Pythagoras to proclaim that somehow maybe you can understand the whole world just through numbers. So this, of course, is the idea that somehow algebra, the manipulations of numbers, the way you divide, multiply, and add numbers must be fundamental to the understanding of the world. So in fact, my point is that even in ancient times, there were possible different points of view as answers to this rather mysterious question. Right? So I thought we'll try to update some of this discussion in a way that we can relate to now. It's very hard to understand the mysticism and metaphorical way of thinking of the ancients, right? But there are aspects in which we can think around the same questions from a modern perspective. So in order to give this discussion some substance, I'm going to start with a rather simple puzzle, right? Having to do with something that's familiar to many of you, description of points in the plane using coordinate axes. I hope many of you have seen this. I'm sure many of you have seen this at some point, right? You can draw axes in the plane and then describe points using pairs of numbers, right? So like that point over there, you might describe as the point 1, 1, meaning you go 1 in this direction and 1 in the vertical direction to arrive at this. So that point is labeled by 1, 1. This point over here will be labeled by 4, 2, and so on. So I hope most of you know this system of naming points in the plane with pairs of numbers. This is the method of coordinates, right? Okay? Good. Now, so here's the puzzle. There's a triangle in the plane, right? And the 3 vertices of the triangle, the points where the triangles end, are at those 3 points, 0, 0, 4, 3, minus 16 fifths, 63 fifths. Right? And the question is, can you say something about the shape of this triangle? What is the shape of this triangle? Now, I'm not asking you to do calculations in your head right now. If you're like me, it's kind of annoying to calculate this. And actually, you're doing something very good. You're trying to draw this out, right? By trying to imagine, at least in your head, what this looks like. That's a very good idea. But in fact, many of the students especially will know that there are other approaches. So in order to figure out the shape of the triangle, what is it good to know? What should we figure out? The shape, we want to know the shape, and in order to know the shape, it might be a good idea to know the length of the sides, right? It might be good to know how long each side of the triangle is. There are 3 sides. So here, there are 3 points, P, Q, and R. So we might want to know these 3 quantities, A, B, C, that are the distances from P to Q, Q to R, and then R to P. So let's try to figure this out. Now, I think you probably have learned this in either middle school or high school. If you just know the coordinates of the points, you can figure out this length. I'll remind you what the formula is, right? In order to figure out the distance A, right? What do? You subtract the coordinates 4 minus 0, square that, subtract the y coordinates 3 minus 0, and after adding those, you just take the square root of the whole thing. So A turns out to be 5. Yeah? Similarly, to figure out B, you subtract the coordinates of R from the coordinates of Q, right? If you do that, again, as I said, you don't have to do this calculation now. You can just take my word for it, that's the correct calculation. You'll find 12 for B, and C, if you do a similar calculation, you find 13. So I think somebody here made a comment. Could you speak up a little bit? It's a right angle triangle. You see that right away, right? So the students here, being very bright, have already figured this out, right? That, in fact, if you take these 3 numbers, you get 5 squared plus 12 squared. In fact, it's 13 squared. You just calculate it, you find it, right? So, according to Pythagoras, in fact, whose picture we saw earlier on, this is a right angle triangle. This is the Pythagorean theorem that, in fact, If you have a right-angled triangle, you get this equality. A squared plus b squared for the two lengths shown in the picture has to equal c squared. But in fact, that's also a sufficient condition for being a right-angled triangle. If you check that equality, it has to be a right-angled triangle. So what's the point of this discussion? Well, I asked you about the shape of a triangle, right? Which is certainly a question about geometry. That's a question about geometry. But we're able to infer geometric properties without drawing any picture. You try to draw a picture, that's a good idea, right? But in fact, you don't need to do that. We just need to calculate. So this is a commonplace elementary thing, but if you think about it, it's quite remarkable. We don't need to visualize anything. We prove a few theorems, and we do a few calculations, and then we can draw conclusions that are of a geometric nature, right? So even though it's elementary, I hope you appreciate simple things like this as a way reflecting some profound aspects of the way we translate different experiences in the world. So in other words, to summarize again, this coordinate system that we're using in order to label points in the plane allows us to encode shapes into numbers and manipulate them and draw conclusions about them. So you may have learned in school, in fact, that using this idea of coordinates, you can represent geometric shapes like circles, ellipses, parabolas, and hyperbolas using equations in the plane, right? So that's pure algebra. If you look at that equation, you're just looking at equalities between quantities, between numbers, right? But that tells you how to describe precise geometric objects like ellipses and hyperbolas, right? So this is the method of coordinates that turns geometry into algebra. Okay, let me describe one other aspect of this translation. In computer vision, many of you in the audience will know this better than I do, but I'm going to briefly discuss it anyways. So what's on the screen is sometimes called the Stanford bunny. This is something people use a lot as a basic example in vision problems, computer vision problems. So that's a photograph that you might pull up on your computer, right? If you have a JPG file, right? Now, if you look inside the file, here's the kind of thing you see. Yeah? As I said, this is kind of a superficial description. Many of you will know this in greater technical detail than I do. Right? But that's what the file looks like if you actually open up a JPEG file. You can go further as well. So there's about, for this particular picture, there's about 12 pages of things like this. I've only drawn a little piece of it. Right? So of course, what you see on the screen, inside the file, besides, if you take away whatever machinery is being used to translate it into an image, it's all just numbers, right? It's all just numbers. So in fact, the key point is that for a computer, what is it to visualize something? How does it store images? It stores a bunch of numbers. How does it turn back into an image that we can see? It does computations. To see for a computer is computations. What about us? What is it for us to see? Well, the point of view, the scientific point of view about this has changed quite a lot over the last few decades, right? But at this point, I think almost anyone would agree, anybody who does serious neuroscience, that is, would agree that for us as well, to see is to compute. So I put up here an excerpt from a History of Cognitive Science by a psychologist named Howard Gardner. He says that central to any understanding of the human mind is the electronic computer. Not only are computers indispensable for carrying out studies of various sorts, but more crucially, the computers also serve as the most viable model of how the human mind functions. Right? Young people probably are especially aware of this basic idea of that the mind is a computer. Of course, then from that point of view, for us to see as well, the light comes and strikes our eye, passes through and hits the retina, and then somehow chemical processes occur and neurons start firing, right? And there's a computation that leads to this experience of seeing, whatever the experience itself is. So we're also computing in some sense with neurons, but neurons from a certain point of view is just another algebraic system of numbers. Okay, so that's about perception, right? But the point of this discussion is that if you think from the point of view of perception, it's easy to see how you might be led to suspect that maybe these computations are more fundamental than the idea of geometry. As far as our understanding, our perception of the world is concerned, it's all computation using numbers of some sort. So that might be one way in which the universe is algebraic. But that's actually only part of the picture. Why? Because you might think, well, that's all fine, but still, that's not about reality itself, right? That's only about our perception of it. What happens in our experience of reality, fine, there's all this computation going on, but surely reality itself is something else. It's not the same as our perception, right? Nobody these days thinks that our perception is all there is. Somehow the world is out there, and we perceive it. And certainly, that latter might be computation, but in what sense could reality itself be algebra? Well, my recent thoughts about this subject were somewhat motivated by a conversation between these two gentlemen, physicists, Sergei Gukov and Robert Dycraft. I'm told that Professor Dycraft was here for a lecture a few years ago, or maybe very recently, I don't quite remember. Right? So he's the director at the Institute for Advanced Study in Princeton, and Gukov is a young physicist at the California Institute of Technology, all those leading theoretical physicists. In 2014, at a conference in Oxford, both of them gave lectures. Dycraft gave an especially philosophical and speculative lecture about the nature of physics and mathematics and the relation between them. He wanted to understand really, well, again, somebody earlier on cited this quotation from Galileo that mathematics is the language of the universe. Right? But somehow not so far from the title of my lecture, some people also sometimes wonder, maybe mathematics is the universe. Maybe the universe is just mathematics. There are people who pose questions or possibilities like that as well. Dycraft's lecture was of this nature. And at the end of the lecture, Gukov asked this question. So in fact, the question of our lecture, in fact, Gukov asked Dycraft, is the universe geometric or algebraic? If you had to bet, what would you say? Gukov likes to express everything in terms of bets, so that's why he asked the question in this way. So Robert Dycraft hesitated a while. Then he said, at the end of this hesitation, after a few moments, he said, well, it seems to be algebraic. Geometry seems to be a kind of statistical phenomenon. So this is rather a striking assertion by leading physicists, right? So just now when we were discussing coordinates, right, we just described the process whereby geometry can be encoded into numbers, right? But what Dycraft is asserting is something more fundamental. Maybe geometry itself arises from something more numerical and algebraic. So that's a more radical assertion, right? So what I'm going to do is spend most of the rest of the lecture trying to give you some sense of what such an assertion might mean, okay? And provide some context to this discussion. So let's start out with a kind of elementary and, in my mind, basic and fundamental discussion of how numbers arise in nature. Well, of course, you may want to know at this point, what do I mean by numbers? Well, numbers, well, the usual 1, 2, 3, 4, and rational numbers, real numbers, these are all numbers. But in a sense, that's not a really essential description of what one might mean by numbers. Okay? I think I forgot to write this up on the slides themselves, so I'll say it in words. So for a mathematician, a number is a number system, are elements of a number system. What do I mean by that? I mean that whenever you can naturally add and multiply a collection of objects, they become numbers. in a certain sense. Whether we give them particular names like 1, 2, and 3 or otherwise, that's not as important as the structure of being able to perform operations on them, adding and multiplying that satisfy certain coherent rules. So from this point of view, let me show you some examples. Yeah, I'm sorry, the pictures are not so good. Those particular pictures were made for a lecture in Korean, so you can see that they're these. Suppose you take 2 points on a line. You're probably well aware of the fact that we can add these 2 points. Well, not exactly. In order to add them, we do need to choose one other point, right? If you choose one point and label it as being 0, that allows you to add any other 2 points. You can see how you would do it, right? It's just a natural process. If this one is called 0, right, to add A and B, we just take the segment from 0 to A and attach it to the segment to B, right? Then you get the segment that goes from 0 to another third point, which is then A plus B. Yeah? This is how you add points in the plane. You don't need to label them as numbers in order to do this, right? This is clearly a natural addition. It's possible to multiply the points in the plane as well. For that, you need one other point. So in other words, we need 2 reference points, one of which we'll call 0, the other one we'll call 1. Then using those, we can multiply any 2 points. So there's a procedure that you'll intuitively see right away, but you don't have to think about it too carefully right now. The procedure is like this. In order to multiply A and B, what do? So we raise one line at right angles to our axis here, above 1, right? And then plot a point on that with the same length as between 0 and A. Then we draw a line whose slope is determined by that length, right? And see where it meets the line that's perpendicular to this one above B, right? Then this length will be exactly A times B. Yeah? So then we lay that back down here. Okay? So again, you don't have to recall this in detail, but it's clear that once you have this reference point 0 and 1, you don't need to label the points any further. There's a natural way of multiplying. So the upshot of the points on the line, in fact, are numbers. Yeah? I'll emphasize again, we don't need to use a separate labeling by number systems in order to do this, other numbers to do this. There's natural ways of multiplying and adding these points. But you can do this with points in the plane as well. This as well, many of you will have seen how to do this. Here we also need to choose an origin, right? But once you've chosen an origin, what happens? These 2 points can be regarded as arrows pointing from the origin to A and origin to B. So to add them, you just take the arrow B and attach it to the arrow A. Then you get an arrow A plus B. This is how you add points in the plane. And similarly, I'm not going to describe this in detail, but you can also multiply 2 points in the plane using this reference line. The rough idea is that to multiply A and B, you add the 2 angles subtended by them from this line, and you multiply the length of the arrows. And then you can multiply, you get a product of A and B. Okay? So, what have we done so far? I've described for you how points on the line are naturally a number system that we can add and multiply. Similarly for points in the plane. Yeah? And this satisfies all the normal rules for addition and multiplication that you're used to. Now, there's another name for the points in the plane that some of you will remember or have seen. The points in the plane, when you add and multiply them this way, this is called the complex number system. Okay? So this will be familiar to some of you. Points in the plane added and multiplied in this natural manner are the complex numbers. Yeah? They were discovered purely algebraically in the 16th century by the mathematician Gardner. But then in the 20th century, something very miraculous happened. Initially, they thought of it as this pure mathematical object. But in the 20th century, it was discovered that when you are describing the microscopic structure of the world, particles like atoms and electrons and so on, in fact, the physical quantities themselves become complex numbers. This was really a miracle in some sense in the history of science. The 16th century discovery of complex numbers for pure algebraic purposes, in fact, was discovered in reality in the 20th century in quantum mechanics. So in other words, what we are trying to say is that these complex number systems are part of nature in at least two different ways. One, they are the natural number system formed by points in the plane, but they are also the fundamental quantities underlying a microscopic description of nature. So these are some examples of number systems in nature. Now, so after I started thinking about these questions rather actively, I also decided to go into a little bit of the history of this subject, right? And there are many different episodes in the history of the interaction between geometry and algebra. That's essentially what I'm discussing with you right now. But there are especially interesting developments in the 19th century that I'll describe for you right now. The first one is due to a mathematician named Hermann Grassmann. So in order to tell you what he did, they start with a question about the ancient Greeks again. I don't know how it was in ancient India, but according to some historians, in ancient Greece, they seem to have had difficulty multiplying four numbers. Nobody here has trouble multiplying four numbers, right? If I ask you what's 2 times 3 times 4 times 5, I hope everybody can do this, right? But the ancient Greeks seem to have had trouble multiplying four quantities. Can you guess why? Sorry? Because they used the geometric approach. Very good. So then what goes wrong with this?
It became extremely complex for them to multiply a lot of numbers. So when the Indo-Arabic numerals were introduced, they found it a lot easier.
That's a very good point. That's probably true as well. But there's even something more fundamental than that. So you're referring to a complexity of computation in some sense. That's true too, right? But some historians say that they had conceptual difficulty that was more fundamental than the computational complexity. Can you guess what that is? That's very close to what you already said. Sorry? XYZ axis. Okay, all of you are giving more or less the correct answer, right? So, but to just summarize the answers you already gave, one way of saying it is that they had difficulty because they couldn't interpret it. You had to somehow interpret the result of your operation, right? So if you multiply two numbers, that becomes an area. Then if you multiply a third number onto that, it should be a volume of some sort, right? But when you multiply 4, it doesn't seem to make sense. So that seems to have been the conceptual difficulty with 4 numbers. It's very related to all the answers that you already gave. I'm just restating it in a slightly different form. Does that make sense? Right. So fine, but we have no trouble now because nowadays we think of numbers in a much more abstract way than they did. We don't need to interpret what we're doing when we're multiplying numbers, right? Somehow it's an operation with a fairly abstract algebraic system. We don't need to interpret it geometry. But this problem itself probably illustrates the extent to which geometry was fundamental for the ancient Greeks. Right. But one of the things that Grassmann did, right? So Grassmann actually was an important figure in many different ways. So for example, some of you who are math majors will have taken courses in linear algebra. Many of the modern concepts of linear algebra were invented by Grassmann. But in fact, he had an algebraic system which turns out to be very fundamental as well. So one way of describing what he did was that he restored the difficulty of Greek multiplication. He made things difficult again. Why is this an achievement? That's a very strange statement, right? What people had grown used to doing easily, he made difficult again. What do I mean by that? Well, what he did was this. So first of all, let me give you this notation, Grassmann multiplication. So he did something called Grassmann, he defined something called Grassmann multiplication. It's denoted by this wedge that's shown on the screen. And what are you multiplying in this case? You're multiplying two arrows. Remember, we represented points as arrows, right? With respect to an origin. So according to Grassmann, how do you multiply two arrows? Well, if you multiply two arrows, remember we said that for Greeks, there's this process of interpreting as an area, right? But here, these arrows also have a direction. Yeah? So if you try to combine the Greek idea of multiplying numbers with the information of the direction of the arrows, there's a natural way of defining the product of two arrows. Namely, you define it to be the parallelogram spanned by A and B. Yeah? So this is a very strange process, but if you think about it for a while, it's very natural. So the product of A and B is simply equal to this parallelogram. So it incorporates information about the area, but furthermore, the geometric information in a more refined way. So this is Grassmann multiplication. The product of two arrows. In modern language, those arrows, by the way, you know are called vectors. That's the language we sometimes use to describe it. There's a sign, that's right. I'm ignoring that right now. You're giving a very sophisticated description that I'm skipping at the moment. That's right. There's also an orientation. That's right. Very good. Okay. But for the moment, let's just say that the product of two arrows is the parallelogram. Okay? Good. Now, so then let me ask you a question. Suppose I take the product of three arrows. What do you think I'll get? Okay, some of you may already know the answer. If you haven't seen it before, it's still possible to guess the answer, right? If you have multiplied three arrows, what you get is this parallelepiped spanned by the three arrows. Okay? As I said, this kind of makes sense, even though it looks a bit strange. So it's called Grassmann algebra, but the other name for it, you can see this makes sense as well, it's called geometric algebra sometimes, right? You turn the geometric objects themselves into an algebraic structure that you multiply. Okay? Now, I'm not giving you the full story, just giving you ingredients of this structure, but it's fun to think about it in this way anyways. So from this point of view, what would happen if you take the product of four arrows? Sorry? You need one more axis, but we don't have it, right? So think like a Greek. You could say there's no answer, right? Yeah? But you're not allowed to do that because we want to multiply everything we want, right? So what's the only possible answer you might give? Sir? Imaginary? Yeah, but what's imaginary? Sorry? So all kinds of sophisticated answers are coming up, but I'm asking for a much more naive answer than what you're giving. We're trying to multiply just three vectors in three-dimensional space, and so the answer in Grassmann algebra, right? Your answers are all possibilities, but the most naive answer in three-dimensional Grassmann algebra is you just take it to be zero. The product of four arrows is just always zero, because that's the modern version of the assertion that you can't take product of four arrows. Right? So you can turn the algebra, the arrows and the parallelograms and parallelepipeds into a kind of consistent algebraic system in this way. Okay, so let me ask another question. So with the information I've given you, again, for those of you who've already seen this, try not to give the answer away to your friends, right? But so if I take the product of two arrows, what do you think you get? Sorry? Sorry, I put it up correctly, I misstated the question. If you take the product of an arrow with itself, what do you get? It should be a parallelepiped, right? But what is the area of that parallelepiped? Zero, right? So the only way to have a parallelepiped of area zero, it again should be just zero. So if you take the multiply two at one, the arrow with itself, you just get zero. That's another aspect of this algebra. Okay? Okay, so as I said, there's a much more rigorous way of introducing this system that I'm skipping right now and just trying to give you a feeling for a bit of the operations. But there are interesting consequences that arise from this already. So for example, so here's a consequence. If you take a product, add two arrows, A and B, and take a product with itself, we get zero according to what we said just now. But if this is a coherent system of numbers, we should be able to expand this as well, right? So this should be A wedge A plus A wedge B plus B wedge A plus B wedge B. But these two end terms are again 0, right? So in a Grassmann algebra, you find identities like this. A wedge B plus B wedge A is 0. In fact. This is related to this direction orientation point that somebody that you raised earlier. Right? So this is an interesting identity that holds in Grassmann algebra. So as I said, at the moment you can take this to be a kind of fun geometric game, but there are serious consequences that follow from it. So what I'm going to do now is show you how this discussion was refined by a mathematician named Clifford, who lived a little bit after Grassmann in the 19th century. Now Clifford, in my view, is one of the most important scientists you've never heard of. That is phrases like this, right? The most important mathematicians you have never heard of, and so on, right? Clifford is one of these characters. He was a real visionary now, if we look back from our current standpoint. So let me tell you just a few things that he did. So that's a picture of him. So he lived, you can see that he died very young, right? He lived in London. He couldn't work at Oxford or Cambridge because he was Jewish. So he taught at the University College London for a number of years, then died at the age of 34, I guess. So if you ever visit London, a very nice place to visit is this cemetery called Highgate Cemetery in the north of London. There are many important cultural figures as well as scientists and mathematicians buried there. The most famous person buried in Highgate Cemetery in London is Karl Marx, the famous communist, but also many famous novelists and poets and so on. And somewhere in there is this gravestone of Clifford as well. That's rather hard to find because, as I said, he's the most important scientist you've never heard of. Other people haven't heard of it either, so it's hard to find this gravestone. But it's there somewhere. And there's a very nice inscription on the gravestone and so on. Both he and his wife were quite important cultural figures in 19th century London, so there's a book about his life together as well. So what did Clifford do? So he actually took Grassmann's multiplication and refined it as follows. So we'll denote Clifford multiplication with a star. Grassmann multiplication was a wedge, right? So what he did is, he defined multiplication. I'm not going to tell you exactly what it is, what the definition was. That will take too much time and development of a subject from the bottom, but I will tell you what property it has. The important property is that if you multiply A and B, then add to that B times A. In the case of Grassmann multiplication, the answer was 0, right? But in Clifford multiplication, it gets modified into something that's called the dot product of the two vectors. Again, many of you will know what this is. If I write down the formula for it, geometrically it's just the length of A, the length of B, and then you take cosine of the angle between them, you multiply all those. That's what the dot product is. And in Clifford multiplication, the property is this strange property that the 0 gets modified by the dot product. So this seems like, again, a very simple and idle thing to do. But what happened in the 20th century, similar to how complex numbers that were discovered in algebra turned out to underlie the physical quantities in the microscopic world, this Clifford algebra, Clifford multiplication, turned out to be exactly the algebra of space-time values of what people are called fermionic fields. So for example, the electron, the physical quantities pertaining to the position and momenta of electron, in fact, are multiplied according to this Clifford algebra. There's one small difference. Instead of just having the dot product on the right, you have this small number called the Planck constant multiplied onto it, which is a tiny, tiny number. So from that point of view, it looks very much like Grassmann multiplication if you ignore this Planck constant and think of it as basically 0. but it's a microscopic modification of Grassmann multiplication in that sense. Right? So, to summarize this a little bit, you could say that Clifford had discovered the algebra of what we now call quantum field theory. This is when we combine the microscopic study of matter, like quantum mechanics, with relativity theory. In a situation where an electron, for example, is traveling close to the speed of light. The study of this is quantum field theory, and the algebra of physical quantities in quantum field theory was discovered by Clifford maybe about 70 years before the subject itself. So it's very interesting that these algebraic foundations come before the important discovery that make them a part of nature. Now, Clifford did a number of other things as well, but one of the very striking things appears in this paper that was published in the Proceedings of the Cambridge Philosophical Society in 1876. The paper is very short. It just goes from here to here. It's basically barely 1 page long. So it wouldn't be regarded as a genuinely scientific publication these days. Why? To have a paper about physics these days, you need a lot of mathematics in it, right? You expect it to have quite a bit of complicated calculations and mathematical structures. But here, this was a more speculative paper that was about 1 page long. But it was called, I don't know if you can see it, it says, On the Space Theory of Matter. So I've excerpted on the next page just some of the paragraphs that appear in the paper. So I'm going to read it to you. Let's read it together. I wish here to indicate the manner in which these speculations may be applied to the investigation of physical phenomena. What were these speculations? That's the part I skipped. In the earlier part of the paper, he discusses the subject of Riemannian geometry. This was the geometry that was discovered by Bernard Riemann in the early 19th century, which you could call, which is normally you refer to it as the intrinsic geometry of curved space. Yeah? For Riemann, he realized that geometry doesn't just apply to the geometry of the space of points and lines and figures in the space we live in, but you can consider any shape you want. For example, the surface of this speaker over here could be itself viewed as a geometric space in its own right. And then how would you discuss the experience of living just on the surface of the speaker? That's the kind of thing that comes up as a basic consideration in Riemannian geometry. So this was at a period when people's conception of what we mean by a geometry was expanding greatly. So Clifford, in the early part of the paper, discusses these developments rather quickly, and then he says, well, he thinks it's going to apply to investigation of physical phenomena as follows. So he says, well, small portion of space are in fact of a nature analogous to little hills on a surface which is on the average flat, namely the ordinary laws of geometry are not valid in them. That this property of being curved or distorted is continually passed on from one portion of space to another after the manner of a wave. That this variation of the curvature of space is what really happens in that phenomenon that we call motion of matter. That in the physical world, nothing else takes place but this variation subject to the law of continuity. Now these ideas, this was 1876, so about 40 years later, maybe I guess around 40 years later, these ideas were systematized by whom? By Einstein. This was exactly what was later called general relativity. General relativity. So that was about 40 years later. And it was turned into a precise mathematical theory capable of giving very new predictions about the structure of the universe. But the ideas surrounding that were already proposed by Clifford in 1876. So it is a very striking fact. So it seems that number or shape or algebra or geometry were things about which Clifford had profound insight, and it's hard not to imagine that he was thinking very deeply about the relations between the two. In other words, about the question that we've asked at the beginning of the lecture. So, somehow, what I'm claiming here is that he was already thinking about the subject of quantum field theory about 50 years before it was properly dealt with by physicists, and also about general relativity 40 years before Einstein. But the striking thing is that even now, we haven't succeeded in reconciling the two. The reconciliation of the theory of quantum gravity, which doesn't exist. That's what people can't figure out. How to reconcile the algebraic description of the microscopic world, right, and the geometric description of the universe at large. And this is what Gukov and Dijkgraaf were discussing as well, actually. They were actually saying, what do you think the structure of quantum gravity should be? General relativity is geometric. The theory, microscopic theory of the universe, as I've tried to indicate to you, is algebraic. If you try to combine the two, which one do you think will be more fundamental? That's the precise nature of the question that they were asking, right? And so, another way of asking the question, by the way, and this is a very nice way, an intuitive way of asking the question that I like very much. This question of the structure of quantum gravity is asking, actually, what is space-time itself made out of? Does that question make sense to you? Yeah. What do I mean? Well, we now know, everybody learns in school, that normal objects are made up of what? Molecules, atoms, electrons, protons, neutrons, quarks. We learn about all these elementary particles that make up matter. We even learn that light is made up of particles called photons, right? But the unresolved mystery is what is space itself, or space and time, or put together, what is space-time made out of? What are the elementary particles making up space-time? What are space-time particles? That is the question of quantum gravity. And the question of our lecture, as well as the question that Gukov asked Dijkgraaf, is the description of space-time particles, should it be algebraic or geometric? What is the appropriate mathematics for that? So that's a relatively precise version of what this whole discussion was about. By the way, so quantum gravity, when it's constructed properly, is expected to explain phenomena like Hawking radiation, which I think many of you have heard about at some point. So far, I've just given you a scattered collection of examples, right, concerning the interaction between algebra and geometry, and how one can sometimes be translated into the other, right, in a description of nature. I thought I'd just elaborate a little bit more on the algebraic nature of the microscopic world. So when you do quantum mechanics, you find out the extent to which it's algebraic compared to our macroscopic theory of the world, compared to when you're doing Newtonian mechanics or general relativity. The algebraic nature, how algebraic quantum mechanics is even shocking a lot of the time. Yeah? And some of you may have taken courses on the subject and have been shocked by it as I have. So here are some examples. So according to quantum mechanics, if you're given a physical system, no matter what it is, physical system means anything, including me, right? Including the light shining from that lamp up there, including the chairs in the room, these are all physical systems, right? And any physical system will be in a state of some sort. So right now I'm in a specific state. If I move like this, I'm in a different state, right? Yeah? And that as I'm moving around, my temperature might be fluctuating slightly, so all of the time my state is changing, right? So a given physical system can be in many different states. But one of the basic principles of quantum mechanics that people struggled with right from the beginning, but the mathematical formalism forces it on you, is that any two states of a physical system can be added in some sense. it's possible to add two states of a physical system, no matter what they are. This is called the principle of superposition in quantum mechanics. So how strange this is, we'll see through some examples of the sort that people are really struck by at the beginning of the theory. So something that you may have thought of, you may have seen, but which on the face of it may not seem so strange, is this was among the early phenomena that people discussed. That if you consider a light source, for example, right, that goes through this first slit over here and the second slit over here, what arrives over here is exactly the sum of the two states that resulted from the two slits separately. So you come upon this phenomena of interference, even when you're shooting just a single photon through the slits. Right? So these were among the early experiments people did in quantum mechanics. So this maybe is far enough from what we normally see in order not to be too shocking, right? But then people came up with examples like this, right? This is called Schrodinger's cat. Schrodinger's cat can be in a dead state or in a live state, right? But according to the principle of quantum mechanics, in principle, it's possible to add those two states and put it into a state that's a sum of the two. It's hard for us to imagine this because this is outside the realm of normal experience, right? But the theory itself allows us to add the two and say that however unlikely it is, in principle, it's possible to have the sum of these two states. Yeah? Let's look at another example. So here are two figures, right? You see, any person is in a certain state of a physical system, right? What distinguished me from the Pro-VC, right, is just the state of the particles that make us up. Basically, we're made of the same kind of particles. You have one collection of states, I have another collection of states. So this gives rise to our different identities, right? But according to quantum mechanics, in principle, we can add our two states and create a superposition. So that's what the theory actually says. Do you believe this? This is unbelievable, of course, and that's why people struggled with these ideas at the beginning. So here, for example, you can add Ramanujan and Einstein. And yet, what would you get? Maybe a perfect scientist or something, right? So all of these are possible according to the principle of quantum mechanics. Now you can ask yourself, what could this addition possibly mean? And that's a good question to ask. I'm not going to explain that to you, but merely say that the principles say that there should be some notion of addition on physical states that make this possible. To just give you a slight sense of what this addition means, one way of thinking about it is that according to quantum mechanics, every state is actually a probability. That's what the addition is about at some level. Every physical state is not something precise, but it's just a probability. So if it's a probability, it makes sense that you can add probabilities, you see, and get a different probability. That's one way of thinking about what underlies the possibility of adding quantum mechanical states of physical system. Okay? So you can imagine creating a state that has the probability half of being the VC and half of being green, for example. That's the rough idea of what this addition means. Now, but what's often, so this kind of thing you'll often read about in popularization of science. The thing that you'll hear about less often is that it's also possible to multiply physical systems. So here, I'll give you just one example. This is in some sense the simplest example. So this is a picture of an electron, right? As you move from left to right, this is the time is proceeding in this direction. An electron comes in and meets with a positron, something that's exactly like the electron but with a positive charge. And when they meet, what happens is that they have a certain probability of annihilating each other, right? And then emitting a photon, or a light ray comes out as they meet and annihilate. So that's a physical process that occurs all the time, actually. The point is, this is multiplication. So we can schematically view this as an electron and positron turning into a photon, but also it's actually a multiplication. I can write this as electron times positron equals photon. That's bizarre, isn't it? Why am I viewing this as a multiplication? Why would anybody view this as multiplication, right? Or I'm also writing it simply as E times this funny times symbol with a zero around it. E times P is phi, we're standing for a photon. Well, at a very superficial abstract level, it makes sense. What is multiplication? It's just something that in abstract terms we sometimes call a binary operation, right? It's something that if you give it two inputs, will produce a single output, right? Yeah. So somehow, it's a binary, this is certainly makes sense as a binary operation. If you input a positron and an electron in a certain state, it will output a photon. So in that sense, it's an operation. So I'm free to call it a multiplication if you want, if I want. But you'd object. Still, multiplication should have certain properties, right? Yeah. So let me, for example, earlier on, in this principle of superposition, we said we can add states of particles, right? So then why is one called addition, sorry, and the other multiplication? It's just arbitrary? You may have wondered this about even elementary numbers, right? When you're adding and multiplying. Adding and multiplying are kind of similar, aren't they, right? Well, you could just as label one as multiplication and the other as addition, just as good, right? They're both binary operations that take two inputs and produce an output, right? So what is the asymmetry in the relation between addition and multiplication? How do you distinguish addition and multiplication if somebody hands to you two binary operations and tell you that one is addition and other is multiplication? I'll give you the answer in this example. So here's the answer. The reason that this process is viewed as multiplication is as follows. Suppose I do the following. Oops. Here, I'm going to take the positron, right? Here in the two pictures, you have the same positron. In other words, the positron states are exactly the same in the two pictures. But I'm going to change the state of the electron. The first state I'm calling is the state called E1, the second state E2. Okay? So I keep the same state for the positron, but change the state of the electron. Then the resulting photon will be in different states. I'm calling it phi 1 and phi 2. Okay? So one could do an experiment of this sort. But you could also do an experiment where you add the two electron states. Does that make sense? Why can you do this? Because we said the principle of superposition says that we can add any two states, right? So these two electron states can be added, and you can bump it into the same positron and see what photon comes out. See? One could actually do this experiment. And when you do it, here's what people find. If you actually did this experiment, the photon that comes out, you'll see will be in the state phi 1 plus phi 2. How you recognize such a state, we're not going to worry about here. There are various experimental procedures for measuring things like this. But in fact, when you put in the state E1 plus E2 with the same positron, the result will be phi 1 plus phi 2. So what are we saying here? Written as an equation, we're saying E1 plus E2 plus P, times P, is E1 times P plus E2 times P. Do you see the point of this discussion? This identity, what is it called? Distributivity, right? That's the relation in a number system. No matter what we mean by a number system, there are two operations, multiplication and addition. And for most aspects, they have the same kind of properties, right? But there's the interaction between the multiplication and addition. They interact, they're not arbitrary, they're dependent on each other in some way. And the interaction is governed by this law, distributivity. Yeah? And in the distributivity, the addition and multiplication play asymmetric roles. Even with numbers, in other words, multiplication distributes through addition, but addition doesn't distribute through multiplication, right? So this identity tells you that in fact, the superposition is addition, and this annihilation of particles business is multiplication. So this is an actual. So in other words, the fact that this process is multiplication is something that shows up in experiments. Okay, so this is another example of how algebraic nature. So in other words, what am I saying here? Elementary particles at the very basic levels themselves form a number system. Okay. Actually, but most of what I described till now, right, is not what I normally work on. No? You may have heard that the title I have in my profession is Professor of Number Theory, no? Which means I normally work on numbers in a very pure mathematical way. So why am I interested in these funny subjects like how you add and multiply particles and so on, right? Well, it's because the basic question in the title of the lecture is something that's very close to number theory. So I can't tell you much about this subject. This is the subject that I actually work on, is something called arithmetic geometry. And by and large, it's even harder to understand than quantum mechanics, in my opinion. So I can't really describe it to you, but I'll give you just a basic flavor of what happens there. So much of the subject was due to a gentleman named Alexander Grothendieck. So so I told you earlier on that Clifford was one of the very important scientists that you've never heard of. Grothendieck was almost certainly the most important mathematician that you've never heard of. He was mostly active in France in the 1960s, and he completely reworked the foundations of geometry and lots of mathematics during that period. But he was also a very strong personality who had strong feelings about politics. In particular, he disagreed with a lot of the funding of academic institutions in France at that time. So he had been working for years in a place called the Institute for Higher Scientific Studies, south of Paris, and he resigned from his positions, moved to a small university, then eventually moved to a small village in the Pyrenees, cut off ties with all his former colleagues, and wrote a lot of things there by himself, but died in isolation. He died just a few years ago, as you can see, so 2014. You know? And this is a picture from the end of his life, which looks very much like a hermit who lives in the mountain, right? That was the nature of his personality. You know? So, but he was an incredibly abstract, he had a very incredibly abstract and foundational mind about how to think about number systems. Number systems are very simple objects in some ways. In the mind of Grothendieck, these were like universes in themselves. Yeah? So the Grothendieck speculations were somehow appropriate to the topic of our lecture. And the point is that in Grothendieck's system, you can start with any system of numbers, right? And starting from a system of numbers, he showed how to cook up a geometric space, a geometric object. So if the system of numbers is called, I've labeled it R, whatever that is, then he showed you how to construct a space called the spectrum of R, with the interpretation that the original number system becomes the collection of functions on this geometric space. So the spectrum of a number system. So I can't possibly describe for you what they are, but I will tell you that somehow, how fundamental it is, you see, this is one of the examples where this process that we discussed at the beginning, where shapes are encoded into numbers via coordinates, is inverted. Grothendieck completely inverted this. He showed how to start from a system of numbers and produce shapes out of it. So what's in the middle here are some of our intermediate examples where the geometric and algebraic nature of an object coexists, like the case of points in the plane or points on the line, right? Then there was the coordinate system where shapes were encoded into numbers. Grothendieck did something extremely fundamental, namely how to produce shapes out of pure numbers. So for example, you can take the usual integers that we study, 0, 1, 2, 3, 4, minus 1, minus 2. So this is the most basic number system, right? And this is the number system that comes up when you study number theory from an elementary viewpoint. But in fact, Grothendieck said that there's a geometric space called the spectrum of Z that we should study if we want to study systems of numbers. That's what I spend most of the time studying, the spectrum of Z. There's a kind of artistic license picture that draws a picture of these kind of objects. You shouldn't take this picture too seriously, but just to give you some sense of the complexity of the geometry that comes out of the spectrum of Z, right? So as I said, but the point is that Grundig and the arithmetic geometers following Grundig became quite used to this idea that geometry can be just generated out of algebra. Yeah? So this question of physicists on whether the universe itself is algebraic or geometric comes very naturally to us. And that's the basic reason for my interest in this question. And it's a reason that I discuss this matter a great deal with physicists these days. For example, we've been having a conference all week at the ICTS, Bangalore, trying to understand the common points of interest of physics and arithmetic geometry. So let's come to the conclusion then. So I may have presented a number of different number systems, geometric objects, and discussions about the complex network of ideas that connects them in a somewhat haphazard way, right? But we can still return to our original question and ask, is the universe fundamentally geometric or algebraic? In other words, is it number or shape? Who was right, Pythagoras or Plato? So the tentative conclusion that I've been describing for you in this lecture is simply that the large-scale structure is geometry, right? And the microscopic structure is algebra. Particles in the microscopic realm form a number system. The structure of the universe in the large is described by geometry according to Einstein as previsaged by Clifford, right? So there seems to be not much more we can say at the moment, and we can't seem to answer this question of which one is more fundamental. And I hope one of you will answer this question, right? I'm too old to think about these questions anymore, right? I can describe them to you and give you my speculation, but I don't think I really have the energy to resolve questions like this. I'm hoping one of you will be able to do it. But there was an interesting lecture I went to this August. So every summer for the last few years, I've been organizing a program, a 2-month-long program at the Korea Institute for Advanced Study that tries to probe exactly this relation between quantum field theory and number theory, my subject. And so I try to bring together a lot of people working in arithmetic geometry following Grundig and physicists to discuss the possible interactions between ideas. And this guy, Nima Arkani-Hamed, came to give a lecture this August. So at the end of a week-long workshop, he came and gave a talk at the very end. So he's a very remarkable personality in fundamental particle physics and string theory these days. So he came at the last day of the conference on a Friday. He arrived by plane from the US to Korea early in the morning, and then he flew back to the US in the evening. So you can imagine how much energy it takes to do that. But he just loves to lecture as well. You know? So he gave the last lecture of the conference and he couldn't stop. It was like scheduled for an hour. It went on for an hour and a half, hour and 45 minutes. And the taxi outside was waiting to take him to the airport, and he was going to miss his flight, but he kept lecturing. So we had to chase him out at the end, because he's such an energetic, charismatic lecturer and personality, laying out all kinds of fantastic ideas about exactly this question: is the universe geometric or algebraic? That really was the subject of his lecture. And his answer was what's shown in this diagram. He felt like that there are some fundamental combinatorial structures governing the nature of the universe, out of which both the algebra and geometry arise. And he told us the reasons that he thinks this. To be honest, I didn't understand his reasons, but hopefully some of you, as you study this subject and go on to try to answer the question in the title of the lecture, will study things like this and come up with answers of your own. So that's pretty much all I wanted to say. But since there are a lot of young people in the audience, let me end with just a minor word of advice and warning. What is the warning about? Well, you see, what did I talk about today? I talked about what you might call very big themes, right? The title of the lecture itself was rather grand and pretentious, you might say, right? Is the universe itself algebraic or geometric? And the warning is that you have to be a little bit suspicious of questions like that. So be careful. It's good to think about this, but you have to be careful not to be seduced entirely by these grand questions, especially when you're young. Why is that? Well, I'll tell you a little story that comes from the biologist named François Jacob. He's a French biologist who received a Nobel Prize in biology, I think in the 1970s, for his contributions to the understanding of RNA helps in regulates gene expression inside cells. Right? So he made some very fundamental contributions to molecular biology. And he has an interesting essay where he discusses, in a somewhat philosophical manner, the development of modern science. And he says very interesting things in there. In particular, what he points out is that the questions that occur very naturally to human beings individually and to humanity as a whole tend to be grand questions. You see? What do we really want to know? We actually want to know answers to questions like, where does the universe come from? How does life arise? What is the meaning of life? Right? And therefore, these were also the question of mythology and mysticism. These were the questions that were asked all around the world. Of course, in India, you have very, very rich tradition of mysticism and mythology, which maybe exceeds that of any place in the world, any other place in the world, right? Which is an important tradition that's very close to our heart as well as close to our mind, right? But François Jacob then goes on to say that these are the fundamental questions that we really want to understand. But that's not what science was about. Science, modern science, became possible when people decided to put these grand mystical questions in suspension. And instead decided to ask questions like, how does water flow through a pipe when you apply pressure to it? How are blood vessels formed through the actions of the heart and interactions with the cell? How does a ball, what kind of a trajectory does a ball describe when you throw it into a air with a certain direction and velocity? These are very specific questions, right? So it's only when the grand questions were put in abeyance and replaced by these specific, concrete questions that science was able to proceed and make progress. And that was the birth of modern science, according to Jacob. But then he goes on to say, the interesting thing is, when people started studying these specific questions and making piecemeal progress in answering them, eventually they found out that gradually that they gained insight on the big questions as well. So now in the 21st century, we can come back and ask questions like, what was the origin of the universe? And begin to provide answers to that are not pure mythology, that can be quantitatively tested, that gives rise to testable predictions and so on, right? Now these questions are scientific questions. The big questions that we wanted to ask before in the mystical age are scientific questions in modern times, and this became possible through our ability to work on the specific piecemeal questions. So it's very important to be able to do that. But as far as the big questions are concerned, so my advice to my students is that you should ask them to yourself about once a year. Because if you forget them entirely, to some extent you can forget the reasons for studying science. So of course, a lot of what really attracts our spirit are the big questions of science. But if you obsess with them, you never make any progress. So you work on your piecemeal problems, try to understand specific techniques, technology, try to find precise answers to questions of everyday life, right? and eventually remind yourself of the big questions at long but regular intervals. So that's the advice I wanted to end with. And in particular, you shouldn't take any of the things I said today too seriously. Okay? Okay, thank you very much.